Welcome back to our second week together. This week begins a very exciting and powerful part of our journey to understand, analyze, evaluate, and translate health system evidence. Because this week, for the first time, we're going to begin to use some descriptive statistics that move us much closer toward analysis of the data. So let's take a look at what some of those are. As you know, we've been working through our Emory roadmap for data-informed health transformation. We are working this week again on exploring data. We'll be focusing on relationships between variables with correlation. So let's look at correlations and how they can be used to help us create questions to guide our analysis. Correlations are very powerful because they help us to relate predictor variables to outcomes that we're interested in. It helps us explore whether or not there's a relationship between a predictor and an outcome. And one of the most powerful ways to begin to look at correlations is with scatter plots. And I hope that you'll see how powerful this tool is as we go along. If we look at this chart, the predictor outcome, as we said, by convention goes on the x-axis, so it's along the bottom, and there's an outcome variable. So as we look at this chart, I'd like you to take about 30 to 60 seconds and pause the video and describe the relationship that you see between the predictor and the outcome. So as you've paused the video and come back now, hopefully you've been able to see that as the predictor variable along the x-axis gets higher, the outcome variable on the y-axis also gets higher. So this line is drawn in the middle of these data points, and it describes a positive relationship between the predictor and the outcome. So let's take a look at another graph. So take, again, another 30, 60 seconds to briefly describe the relationship you see between this particular predictor and outcome. And as you've looked at these data, you've probably noticed that there's a negative relationship now. This line that goes to the middle of the data points indicates that as the predictor variable gets higher, the outcome variable actually gets lower. So that's a negative relationship. Now let's look at a third common experience between predictors and outcomes. And in this situation, what type of relationship do you see? Pause for a second and come back and join us. So as you've looked at the data here, you've probably noticed that there's essentially no relationship between the predictor and outcome. It's not possible to draw a positive line through these data, or a negative line through these data, or an arc, or any type of shape that would summarize the relationship. So with that in mind, those three primary relationships, there's certainly many more, those three primary ones will carry us through 80 to 90% of our work with statistics and analyzing data for health transformation. So let's talk for a moment about Pearson's correlation coefficient. In the previous diagrams that we had showing the relationship between a predictor and an outcome variable, the first two, can you summarize how the relationship between the predictor and the outcome is demonstrated? So if you thought about that, you'll probably realize that for both the positive and the negative relationships, it was essentially a line. And the first one, as the value of the predictor increased, the value of the outcome also increased. In the second graph, as the value of the outcome decreased, the value of the predictor increased, and that showed a negative relationship, but both of those were linear. So it's characterized by a straight line between the two. So The challenge and the yikes comes back to us again if we have data that are not linear. What do we do with those data? How do we handle them? How do we understand them? Can we describe a relationship between them or not? And fortunately, there are many tools, and one of the most powerful and most common is the Spearman's rank correlation coefficient. So we talked a moment ago about the Pearson's correlation coefficient, one that shows relationship between variables when the relationship between them is close to a straight line. But when that's not the case, we have the Spearman's rank correlation coefficient. And I'd like to demonstrate this coefficient by looking at this graph, or rather by looking at this table. These data summarize a very small sample of people whose intelligence quotients were measured. And here you have the response. Person number 1's intelligence quotient was 86. Person number 2's was 97, and so forth down the list. Now, if we wanted to see if there was a relationship between intelligence quotient and the number of hours of television that an individual watched in a week, we could do it using a Pearson's correlation if there's a linear relationship between these two variables. But just for the sake of discussion for a moment, let's assume there is not a linear relationship. So that as the hours of TV watching along the x-axis increase, there's no clear increase in intelligence quotient or no clear decrease in the intelligence quotient. So how can we describe the relationship between these two variables? The Spearman rank correlation coefficient does not use the actual score for either variable. Now Pearson, where we had the blue graphs at the beginning, plots the intelligence quotient on the bottom, or rather the hours of television watching on the bottom as a predictor variable, and the intelligence quotient going up the y-axis as an outcome variable. And the hours of television watching would also be converted into a rank score. So instead of using the actual number of hours of television, we would consider how each value is related to the others, and we'd rank them from lowest to highest. So as you see in this iteration of the table, we've ranked intelligence quotient from the lowest of 86 to the highest of 110. That's rank order 1 through 8. Now for each person, we've also ranked their hours of television watching. In this case, the hours of television watching are not already in rank order. So here the person watching 0 hours ranks 1, and the person with the most hours of television watching ranks 8th. And so what what the Spearman rank correlation coefficient does is, instead of comparing the actual value, it uses the ranks. And it compares. So for example, for this person, their intelligence quotient is the lowest, and their hours of television watching are also the lowest. For this person, their intelligence quotient is ranked second lowest, and their hours of television watching are fourth lowest. So you compare rank to rank instead of score to score. And so this method of comparing ranks across variables as opposed to the actual score is non-parametric. It doesn't matter if the underlying variable is normally distributed or left skewed or right skewed or bimodal, because this rank order has no relationship to the underlying data distribution. So that's one of the reasons it's called non-parametric. It's not specific to a data distribution. And so this is a powerful tool for describing data that are not normally distributed. So I think this illustrates how powerful and important it is to check the distributions of the data before we run analyses. If we had run Pearson's correlation coefficients on data that were not normally distributed, we would have gotten an answer for that statistic, but it would have been essentially meaningless. And we'll go through and demonstrate this with some SPSS examples in a later discussion this week. But the second point that is crucial to realize is that the assumptions of the statistics are the guide for our analysis. And just like Pearson's correlation coefficient assumes there's a linear relationship between the variables, and Spearman's does not assume any relationship between the variables, that assumption impacts the interpretation of the statistic. So simply running a Pearson correlation coefficient on two numbers could be completely meaningless, even if we get a value for that statistic, because we have to understand the underlying distribution of the data in order to effectively select the test that's going to help us to answer our practice question. So in our talk so far, we've looked at the relationship between variables. We've considered how the relationship between them is important and is really the key to getting started on our statistical analysis journey. We also, in our SPSS analyses, will see how the magnitude of relationship, how strong a correlation coefficient is, whether it's positive or negative, can also help us to understand the relationship between variables. So join us for probably the last part of our time together this week, probably part 4, where we run through some SPSS examples together to demonstrate these principles. So best wishes for your data analysis week ahead. I look forward to seeing you in our next session.